Good morning, my name is Luca and I'm part of the SD Lab. My thesis title is Development of Framework for Coupled Aerostructural Optimization of New Generation Wings that I'm doing under the supervision of Professors Rauno Cavallaro and Andrea Cini. The motivation is linked to sustainable aviation that can be achieved via improving the aerodynamic efficiency of the airframe, for example, with the larger aspect ratio wings or with a new concept like truss behind the wing of the aircraft. In general, this always implies a more complex optimization problem because the structure and aerodynamics are more coupled. That's why we, together with the other problems, we cannot rely always on old tools and on legacy methods for optimizing in a proper way the design. So the connection from sustainable aviation to sensitivity computation passes through the fact that a new configuration or a complex system is described by a large number of design variables, for which we can, for example, use the gradient-based method for optimization. And in turn, for this method, we need an accurate evaluation of the sensitivities that can be done, for example, with the adjoint method and algorithmic differentiation given the large number of design variables. So the question that links to the methodology is how to compute accurately the sensitivities of a coupled aerostructural system. Before, I want to illustrate briefly the state of the art. So looking at the literature, it was clear that algorithmic differentiation is already effectively used in sensitivity analysis for finite element solvers, but the problem is that the models are of moderate size. That means it's impossible to assess the overhead in terms of memory and the time consumption, which is very important. And this is the first gap we try to fill. Then, in general, there are many parallel solvers that rely on algorithmic differentiation for CFD adjoint solvers, but we couldn't find an analogous implementation for finite element analysis, and this is the second gap we try to fill. And then for what concerns the aerostructural optimization, it is a very popular field, but in general, we could detect that the stress constraints dominate the optimization. Buckling usually introduced in a simplified way, and rarely the effect of the deflection of the structure on the modal buckling behavior is considered. That's why we also decided to try to fill this gap. In general, the thesis contributions can be summarized in three parts. The first part was to implement the structural size optimizer with stress, model, and buckling constraints. Second part was all the work related to the computational performance of the solver concerning memory, scalability, runtime, and so on. Third part, that is the one I'm focusing now, is on the aerostructural optimization itself, and will be probably part of the next journal paper. The impact is to contribute to the design of high-fidelity, large aspect ratio, new generation wings. So the framework we are talking about is composed by SU2 as a CFD solver, by our in-house code Augusto for finite element analysis. They are high fidelity, so CFD and geometrically shell-based elements. They are differentiated with the Codipac library for consistent derivatives evaluation. They are parallelized with the MPI for large-scale problems, and the idea is to deal with a general problem with aerodynamic and structural design variables, and with purely aerodynamic, purely structural, and also coupled objective. To illustrate the methodology, we can focus on a mass minimization problem. The constraint is the satisfaction of the coupled aerostructural system, whose equations are determined by capital G. And then a set of optimization constraints, small g, can be, for example, stress and modal constraints. So in the coupled system, apart from the aerodynamic equations and the structural static equation, we have also the eigenvalue problem, the mesh deformation problem, and the scheme for the transmission of loads and displacement between the two meshes. The computation of the gradients is based on the adjoint method and algorithmic differentiation. We consider to compute the gradient of a response that can be the objective or a constraint that we call J. We introduce the Lagrangian, so we incorporate capital G in a single expression through the adjoint variables. Then we take the derivatives with respect to the state variables, and we get a set of adjoint equations. In this case, I have only written the aerodynamic and the structural part of the equations. And then if we compute the gradient with respect to the design variable, we get the expression of the gradient of the response that we are interested in. The procedure is the following. So for the current design, we solve the equilibrium equation of the structure under the aerodynamic load. Then we we record the computational path of the primal solver. That is a part that allows the solver to compute all the partial derivatives that appear in the adjoint equations. And then we solve the adjoint equations sequentially, one after the other, for a certain number of adjoint fluid structure interaction iterations. Upon convergence of the adjoint variables, we can compute the gradient of the response we are interested in. The test case I'm mostly focusing on is the NASA Common Search Model. It has 113 thickness variables that are the colored boxes you can see in the lower picture. Then we consider two constraints: the aggregation of the von Mises stress on the upper skin, and the frequency spacing constraints that control the distance between the two first frequencies. I've only recently started to get some results that are quite premature. Test one is we consider stress and the frequency constraint together. The mass has this oscillating behavior, probably for a problem of swapping of the frequencies, while the second test went better, even if basically all the same variables got to the lower bound. To conclude with the achievements of my PhD up to now, recently an article was accepted for a journal. Then I have two conference papers for the Arobest conference in 2023 and 2025. And then in 2024, I was in Germany for the research stay, during which I developed all the part concerning the eigenvalue sensitivities. Thank you.